Part 2, Sound Frequency.
Besides sound pressure, the most important other property of sound is sound frequency. Frequency refers to how many pressure oscillations or complete wave cycles do we have per second. The internationally accepted unit is the Hertz, named for German scientist Heinrich Hertz, abbreviated capital H small z, with 1 Hertz being equal to 1 cycle per second. The human hearing range is from approximately 20 Hertz on the low end to 20,000 Hertz on the upper end, although in actual practice a great many people can't hear sounds anywhere near 20,000 Hertz. As one ages, you lose those very high frequency sound hearing abilities rapidly, so many people can't hear sounds above, let's say, 12 or 15,000 Hertz, but it's really not very important for most purposes. Sound can exist beyond those ranges, it's just that we can't hear it normally. The region below 20 Hertz is referred to as infrasound, and the region above 20,000 Hertz, abbreviated KHZ for kilohertz, is referred to as ultrasound. These have important purposes, but they're not related to hearing. Our hearing is not equally sensitive to all frequencies within the human hearing range. We have a peak hearing sensitivity around 2 to 3 kilohertz, 2 to 3,000 Hertz, where our ears are tuned for most amplification of the sound. Higher frequencies and lower frequencies, the hearing ability falls off. And lastly, I want to mention that the subjective indication or sensation of frequency is pitch. We can't directly experience those oscillations per second. They happen too rapidly. Instead, we perceive them as pitch. Low frequency is low pitch. High frequency is high pitch. Sounds that only have a single frequency are referred to as pure tone sounds. These are not too often found in nature, but they are sometimes found in music, and they're what we use for hearing testing as well. Here's a couple of examples of the graphic representations, and you can also hear the pure tone sound. The top picture there is of a 220 Hertz tone, which sounds like this. And what you're seeing is 2 1/100ths of a second of the pressure wave associated with that tone. Since it's 220 Hertz, it's fluctuating up and down 220 times per second. So there's 4.5 or so oscillations in this 2 1/100th second period. The bottom representation shows pressure versus time for a 440 Hertz tone. Twice as many oscillations per second, but what you hear when I play you the tone is a sound whose pitch is higher than the 220 Hertz tone. We can't perceive the 440 pressure oscillations per second. What we hear is a tone of a certain pitch. Mixtures of pure tones are more common in reality. Musical notes, insect calls, things like that, even human voices are pretty much mixtures of tones. You can see from the graphs here on this page that the pressure versus time pattern is a little more complicated, although it still has the same basic repetition that you saw in the pure tones. The first one there on top is the mixture of the 220 and 440 Hertz tones that we heard in the previous slide. So you can see how that sounds. Because those two tones are so close together and one of them is twice the other one, they sound pretty good together. They don't sound harsh or clashing or anything. The second graph that we have there is the same 2 1/100ths of a second of that little ding sound that you hear at the end of each slide. A little more complicated than the two tones, the 220 and 240 that we heard at the first. So just to remind you, here's the little end of slide sound, but it's not really the end of the slide this time. And the third graph is of my voice saying the number 1, again with just a 2 1/100th second snippet taken out there. And you can see that there's the same sort of repetition, but a little more complicated, because vocal tones are mixtures of many different tones, not just 2 or 3 or 4. So it gets more complicated, and there's a certain amount of randomness in there as well. Another category of sound is what's often called broadband noise, or just sometimes noise. Like the mixture of tones, this is many frequencies mixed together, but the difference is that it's essentially all different frequencies with a random probability of any particular frequency at any given moment. There's also a random fluctuation of the sound pressure level. You get the kind of display that you see there at the bottom. Again, that's 2/100ths of a second of a noise rather than a tone. So it's very irregular. The peaks are quite unpredictable, and in fact for random noise they're completely unpredictable if it's truly random. Now there are many sorts of noises, but there are a couple of them have names. One of them is white noise, in which all frequencies have an equal probability of taking place. And here's what white noise sounds like. Sort of like rain on the roof or radio static or something like that. Pink noise is a special kind of broadband noise, which has been weighted toward the low frequencies in such a way that each octave band of sound will have the same sound energy. Now, I know we haven't talked about octave bands yet, but that'll be coming up. Pink noise is very often used for testing sound systems and for any sort of acoustical testing. Here's what pink noise sounds like. Both white and pink noise are merely examples of specific kinds of noise. Many things that we hear in real life are broadband noise, traffic noise, machinery noise, things like that, although in some cases there may be a mixture of random noise and tones. The pressure versus time graphs that you've seen on the previous slides are not the usual way of displaying the information. Usually we use what's called a spectrum, in which the sound pressure level at various frequencies is plotted as a graph or as a table. This is a more convenient way to give the information about sound level and frequency. The graph on the bottom left there shows a complicated graph of sound pressure level versus frequency, in which you can see all the minute fluctuations. That's one approach. The other approach is on the bottom right, where we see frequency bands or frequency groups, and we just give the information in sort of a relatively crude fashion. At this band of frequencies, here's the sound pressure level. At the next one, here it is, and so on. For many purposes, the simpler presentation there in the lower right is quite adequate. Alternatively, we can simply give it as a table, but sometimes it's helpful visually to be able to look at the graphical display of frequency versus sound pressure level to make some judgments about the sound. For doing calculations, a table is probably easier, so that's what we'll be using most of the time. Virtually all spectrum displays are done with frequency bands, but there's a wide variety and choice among the bandwidth. One possibility is to use constant bandwidth, whether it's 1 Hz, 10 Hz, 100 Hz, or whatever. This is sometimes done particularly for narrow regions of frequency where we want great precision. More common in acoustics is to use what are known as constant percentage bandwidths, in which the width of the band, the frequency region we're looking at, is some constant fraction of the center frequency. The octave band, the most common constant percentage band, has a width approximately 71% of the center frequency. Third octave bands are used for greater precision, and these have about 1/3 as wide, so that's about 0.235 times the center frequency. And sometimes other bands are used, 1/10 octave or 12th octave, for even greater precision. But the great majority of acoustic work is done with octave bands and 1/3 octave bands. The octave band is the most common bandwidth that we see in acoustical work. An octave is defined as a sound region in which the upper frequency is 2 times the lower frequency. In musical terms, if we go on a piano, for example, from one A note up to the next A note, then we've doubled the frequency of the note. The center frequency is defined as the square root of the product of the upper and the lower frequencies. Any octave band could be used, and any center frequency could be used. For standardization purposes, we have certain standard frequencies that all instruments use and everyone uses by convention. These are the frequencies starting at 16 Hz and going up to 16,000 Hz, so it covers the entire human auditory spectrum. You'll notice that it's not precisely twice each time, 16 to 31 to 63. It's actually 31.5, but it's close enough so we don't worry about the small fractions of a hertz. And in fact, most acoustics work is done in the 125 to 8,000 hertz bands. Using these standard center frequencies, we can determine the upper frequency of each band as 1.414 times the center frequency, which is the square root of 2 times the center frequency. And the lower end of the band is the center frequency divided by the square root of 2, 1.414, which is the same as multiplying by 1 over the square root of 2, which is 0.707. So, for example, the 1000 hertz band goes from 707 hertz to 1414 hertz. The upper frequency is twice the lower frequency. The 2000 hertz band would be from 1414 to 2828 hertz. So you see there's no gap between bands. We're covering the entire audio spectrum by means of these octave bands with no gaps in between. Now, this is not the sort of thing that one needs to keep in mind all the time. What's really crucial here on this slide are the standard center frequencies. If you start at 1,000 and double each time, or start at 1,000 and divide by 2 each time, you get all the standard frequencies. So they're relatively easy to remember. Although it's very useful to have the sound spectrum, there's sometimes when that's more information than we need. Sometimes all we want to do is combine all the sound levels and the frequencies into a single number, the overall sound pressure level. When we do this without making any distinction among the different frequencies, this is called the unweighted sound pressure level. All frequencies within the human hearing range are included. More common is to use what are known as weighted sound pressure levels, where we give different emphasis to different frequencies depending on how we hear them primarily and what our purpose is. The most common kind of weighting is what's known as A weighting. There are others. B weighting and C weighting have been used in the past quite a bit, and C weighting is still used frequently. Other weighting schemes have been proposed, D weighting, and I suppose some others. But by far the most common is A weighting. So most often noise measurements, whether explicitly or implicitly indicated, are in terms of A weighting. So let's go into how A weighting is done. The great virtue of A weighting is that it simplifies our measurements. Instead of having to have a full spectrum to deal with, we have a very simple procedure which allows us to use a single number to characterize a noise. Fortunately, A weighting correlates reasonably well with hearing loss risk and also with more subjective factors such as annoyance, sleep disturbance, and speech interference. Back when weighting schemes were first utilized 30, 40 years ago, something like that, the intention was to use B weighting and C weighting also for these purposes under different circumstances. However, A weighting has come to be the de facto standard and is nearly always used. The table that you see here gives the weighting factors for different frequencies. At 1,000 hertz, there's no correction factor. As we go to lower frequencies, the correction factor increases. At 500 hertz, it's approximately 3 decibels. To be precise, it's 3.2, but we really don't need to be quite that precise. At 250 hertz, it's approximately 9 decibels, and so on. This accounts for the fact that we don't hear low-frequency sounds as well as we do the medium high-frequency sounds like 1 and 2,000 hertz. In fact, we hear 2,000 hertz a little better than 1,000, so it gets a plus 1 decibel correction factor. 4,000 gets plus 1. And then as we go to higher and higher, our hearing begins to slip off a little bit. So at 8,000 hertz, there's a minus 1 correction factor. And if we were to look at even higher frequencies, we would see an even greater correction factor at those frequencies. Although A weighting is used most of the time, occasionally we use C weighting as well, particularly when we want to cover the full audio spectrum without giving any particular weight to one portion or the other. One primary use for this is for hearing protector assessment. If we measure the noise exposure using C weighting, we can apply the noise reduction rating that is given for hearing protectors directly to the sound to determine the protected level at the ear. Another use for C weighting is in what's called the AC difference, measuring the sound level using A weighting and C weighting, determining the difference, and estimating the frequency. The weighting factors for C weighting are, as you see on this table here, and they're pretty much non-existent compared to the A weighting factors. From 63 Hz all the way to 4,000 Hz, there's less than 1 decibel correction factor. Only when we get to 8,000 Hz on this chart do we have a significant correction factor of -3 decibels. When we look at all the sound frequencies taken together, we call that the sound pressure level. When we apply weighting, we call it the sound level without the term pressure. And we designate the unit with the appropriate symbol, the A or the C. Very often you see the unit written as dBA or dB and then A in parentheses. The standard method these days is to write it as L sub A, where L stands for level and A is the weighting factor. You could also have L sub C, of course. If you see L sub P, the P stands for pressure, and so that's the sound pressure level. So L sub A equals 80 dB, or 80 dBA would be equally satisfactory, although the L sub A method is preferred. I mentioned earlier using the difference in the A and C weighting to estimate frequency, so here's an example of that. Let's suppose that the C weighted sound level minus the A weighted sound level is 10 decibels. If we look on the chart below, which shows the A weighting on the middle row and the C weighting factors on the bottom row, we see that there's a difference of approximately 10 decibels at about 250 Hz. The C weighting is 0, the A weighting is -9, so that will give us approximately 10 decibel difference. Therefore, we're going to say the predominant frequency of this sound is about 250 Hz. This is a relatively easy way of estimating the frequency without going to the greater trouble of determining the full sound spectrum. I should probably mention another use for C weighting, and that is to simply get one into trouble. Most instruments have a switch that allows you to measure either A or C weighting, and it's easy to make the mistake of having the switch in the wrong position. So when you think you're measuring A weighting, which is done most of the time, you might be actually measuring the C weighting. And as you see from the chart, if the sound is of a particularly low frequency, you can make a very large error in this case. Many industrial sounds, the A-C difference is 5 to 10 decibels. It's important to make sure that when you think you're measuring A weighting, that you really are, and you have the instrument switch in the right position. Let's look at how weighting is used as an estimate for the loudness of sounds. The loudness involves both the sound pressure level and the frequency distribution of the sound. So actually to calculate loudness, which has the unit of tones, is somewhat complicated, but we can do this in a simpler way with A weighting. Let's consider, for example, a sound pressure level of 115 decibels. Is that a loud sound? Well, the first instinct would be to say yes, that it is a loud sound, but we really can't be sure about that unless we know the frequency content. So what if I told you it was 115 decibels at 30,000 Hz? Well, that would be in the ultrasound range, and even though there's a lot of sound energy there, it would be inaudible and therefore not loud. So let's now change it to 115 decibels at 3,000 Hz. Since that's right at the area where the ear is very sensitive, that would be a very loud sound. Next, consider 115 decibels at 30 Hz. Now that's within the human hearing range, but because the ear is less sensitive, it would be considerably less loud than the 115 decibels at 3,000 Hz. So you see that this is all complicated and depends on the frequency, and I'm giving you examples here with single frequencies. What if you had a range of frequencies? How would that affect things? The simplified method is to use dBA. So if we say 115 dBA, then the A weighting includes both the sound pressure level and the human hearing response. So we can say this is clearly a loud sound without having to know the frequency distribution of the sound. Most of the time when we're trying to do A weighting, we don't have to worry about what the correction factors are, because the sound measuring instrument will do the A weighting for us electronically, automatically. All we have to do is have the switch in the right position. This is a very simple thing for the sound measuring instrument to do, because it's simply a matter of a few resistors and capacitors arranged appropriately to do the weighting. It's not like there has to be some computer doing it. It can be done by a simple network of resistors and capacitors. Sometimes, however, we have to do it by calculation from octave bands or possibly even from third octave bands. So the procedure here is simply to take our octave bands, which are typically unweighted, and then subtract from them the A weighting factors, as we've done in this example here. After we've done the subtraction of the A weighting factors, and we have now the weighted octave bands, 49, 59, 61, and so on, we add those up as we do ordinary decibel addition to come up with the A-weighted sound level, simply by adding together all those 8 different weighted octave band levels. Adding those A-weighted octave band levels up will give us an answer of approximately 73 dBA. You might try that yourself as a check. Here's an example of how we use A-weighting in noise control procedures. We could simply measure the A-weighted sound level of 73 dBA, but if we want to be able to calculate what it will be after we apply noise control procedures, we have to measure it using octave band analysis. That's what we've done in the top 4 lines here, in which we get the blue shaded octave band results, which add up to 73 dBA. This is also a good check on the actual measured sound level in A-weighted as well. They should be within 1 decibel or so. The key point here is that we're now applying some noise control measure, or at least we're planning to apply some noise control measure, and the effect of that is shown in the tan box with different amounts of improvement at different frequencies. Very commonly, the low frequencies will have less improvement than the high frequencies, and so that's the example I've shown here. So we have 5 decibels of improvement at 63 Hertz, 10 decibels at 500 Hertz, up to 20 decibels at 8,000 Hertz. We subtract those numbers from the A-weighted octave bands, and by the way, we just use ordinary subtraction, as I presume you've already noted here, and so we get the weighted octave bands that would be predicted are in the green band there. We add all those together, and that comes up to 61 dBA. Our projected improvement by making our changes, which lead to all these different octave band changes, is from 73 to 61 dBA. This is just an example to show you how we can predict the A-weighted sound level, which is usually the thing of most importance, by looking at the octave bands, seeing how much improvement we predict in each one of those, and going through our calculation. Let's take a moment to summarize what we've covered about sound frequency. Frequency as the unit of the hertz, with a human hearing range normally expressed as 20 Hertz to 20 kilohertz, although in actuality many people can't hear above 12 or 15,000 Hertz. The ears have a maximum sensitivity around 2 to 3,000 Hertz, and the sensitivity drops off as we go higher and lower than that. We can classify sounds according to their frequency content as pure tones, mixtures of tones, and broadband noise, plus perhaps a combination of noise and tones. The spectrum is the display of the sound pressure level in decibels versus the frequency in hertz, which may be done either graphically or in table form. Most often we do spectrum analysis in octave bands. The octave bands are set up with standard center frequencies of 1,000 Hertz and then doubles and halves of that, so 1,000 Hertz, 2,000, 4,000, and so on, and going lower, 500, 250, 125, and so on. And lastly, we talked about sound weighting, A weighting and C weighting, with particular emphasis on A weighting, which is most commonly used to approximate loudness, to allow us to estimate the potential for hearing loss, annoyance, many different types of subjective response. It combines sound pressure level and frequency distribution in a simplified way.